All right, let's look at the questions from the Chapter 14 review, which is on page 711. And the first one we want to look at is number 2. Number 2 says, if a single card is selected from a standard 52-card deck, what is the probability that a red face card is selected? So the probability of a red face card. Well, we know that there are 52 cards in the deck, so our denominator is going to be 52. And then we need to find out what our numerator is. So if you remember back, if you go back to your block, within the chapter folders, within the Chapter 13 and 14 folder, there is a document called Sample Spaces, where I have what all the playing cards are, in case you aren't as familiar with playing cards. And we have a red face card. Here's all the red cards. And the Jack, Queen, King are considered the face cards. So notice there are 3 of each of those, so there's 6 total that are red face cards. So what we're going to do is we're going to put a 6 in there for our numerator. And then we can simplify that. We see that 2 will go into both of those, so that would leave us with 326. And you could leave your answer like that, or you could turn it into a decimal. Either would be fine. So that's number 2. Number 7 says, if a single card is drawn from a standard 52-card deck, what is the probability that we will obtain either a face card or a red card? Okay, a couple ways you could do this. Probability of a face or a red. Anytime we have this or in here, what we could do is we could say that's the probability of a face plus the probability of a red minus the probability of both. Because what we're going to do is we're going to end up overcounting. So the number of face cards that are total, well, there's 3 in each suit, so there's a total of 12 face cards. So the probability of pulling a face card is 12 50-seconds. Plus the probability of pulling a red, well, 26 of the 52 are red. Minus the probability of a red face, well, we found up above, is 652. So 12 plus 26 minus 6 is going to give us 32 50-seconds. And then we could divide both of those by 4, and that will give us 8/13. Okay, so that's your answer. Or the other thing you could do is you could say, let's count up the face or red, and you could go back and just carefully count those. But I think this is probably the easiest way to do it. All right, number 10 is next. So on number 10, it says, if a pair of fair dice is rolled, what is the probability that we will roll a total of 5 if we are given that the total is less than 9? So the probability of sum of 5 given that we have a sum that is less than 9. Now, anytime, and this is a conditional probability, so anytime we have a conditional probability, what I do is I start by looking at what is our new sample space. So I'm going to go that sample spaces document that I have in there. And typically when we're rolling 2 dice, we have all of these possibilities, 36 possibilities. However, we are told that the sum is less than 9, which means that we can knock out some of this, some of these numbers. So we can knock out this 10 here, this 10, and this 11, this 10, this 10, 11, and 12. And it says the sum is less than 9, so actually we could knock out all the 9s as well. So we can knock out all of these 9s. Come on. And now our sample space is just what's left, right? So we knocked out 1, 2, 3, 4, 5, 6, 7, 9, 10 out of the 36 that we started with. So we only have 26, and that's going to be the denominator of our percentage. All right? And so I noted that on my paper, and I'll get back to that in just a second. And now we want the probability that we have a sum of 5. So the ways we could get 5 are 1 and 4 right here, 2 and 3 right there, 3 and 2, and 4 and 1. So there are 4 ways we could get a sum of 5. So when I go back, there are 5 ways that I could get a sum of 5. And my sample space, if I was just looking at stuff that was less than 9, has been cut down from 36 down to 26. All righty. Wait a second, that's not 4. That's 4, I'm sorry. Because sum of 5 would be 1 and 4, 4 and 1, 2 and 3, 3 and 2. Sorry, can't count. Okay, so that's 426. So that would simplify down to 2/13. Okay, number 11. Number 11 says, assume that 2 cards are drawn without replacement from a standard 52 card deck. What is the probability that 2 hearts are drawn? So probability of a heart followed by another heart. So the probability of the first heart, well, we have 52 cards in that deck, and 13 of them are hearts. Times, since these are done sequentially, we're always going to multiply those. We have to get a second heart. We already pulled the first heart, so the probability of the second heart, well, we only have 12 hearts left out of 51 cards that are left. And now I want to simplify that, so let's see here. This would simplify down to 1 out of 4. This would simplify down to 1 and a 3. And this would simplify down to a 1 and a 17. So we get 1/17. So that's part A. Part B says, what is the probability that a queen and then an ace is drawn? So the probability of a queen and then an ace. So the probability of a queen, well, there are 4 queens out of the 52 cards. And then we've already pulled a queen, so there are 51 cards left, but there are still 4 aces. So we can do a little simplifying here. That would be a 1 and a 13. And then we just multiply straight across. So we get 4 and then 13 times 51 gives us 663. So that's our probability of pulling a queen followed by an ace. Now the last one we want to look at is number 15. And number 15 says, a card is drawn from a standard 52 card deck. If a face card is drawn, you win $15. Otherwise, you lose $4. Calculate the expected value for the game. So anytime we're dealing with expected value, we need to look at what our outcomes are, what the value of that outcome is, and what the probability of that outcome is. So in this game, we have 2 outcomes. We could draw a face card, or we could draw something that's not a face card. The value of drawing a face card is $5. The value of drawing a non-face card is minus $4. And now we need the probability. The probability of drawing a face card, well, we did that up above. Probability of a face card is 12 out of 52. And if there are 12 face cards, that means there's 40 non-face cards, so the probability of drawing a non-face card would be 40 out of 52. And then our expected value is going to take each of these outcomes, multiply the value of that outcome times the probability of that outcome, and then add those together. So the expected value would be, we take the faces, value of a face is $15, times the probability, 12 52s, minus 4, we're going to add, but it's a minus 4, times the value, or the probability, which is 40 52s. And then I'm just going to do that on the calculator. 15 times parentheses 12 divided by 52, close parentheses, minus 4, parentheses, 40 divided by 52, close parentheses. And I get expected value is about 0.3846. So we could round that off to about 38 cents. What that means is, if you were to do that experiment over and over and over again for a huge number of times, that in the long run you would average walking away with 38 cents. Sometimes you'd walk away with 15, sometimes you'd lose $4, but if you were to average everything out over a long time, it's going to average out to being on the plus side by 38 cents.